There's no current here.
Five divided by 10.
No.
It's like,
Well, I'm gonna write it because we have positive. So when you say the exit value is the current.
the same, but it would also be the what happened.
And that's nice. And then you count
That makes
so I plus I add. All that.
Oh, I get so
And we also got
I feel like overall, Eastern series that is a common so how you have your house and stuff for sure. Like my welding today, I'm shitty. I was in a hurry, that's why. That one day I missed out. That's different. Oh, the first game was totally worth it. No, I need a knife. Oh, that's me every day. I did a nice one.
Hey, shall we do this now? Let's look at this. So there's actually 3 ways to do this problem. I found that the people that did it with Node were highly unsuccessful, except that there's a few that actually did it with Node and it worked out. But most of the people that tried it weren't even close. And one of the reasons why is that note that this output is your voltage source. Right? It's, remember, when I'm talking about, can I write an equation for this B source? Can I do node analysis on that? You can't. So I can't apply node at here or there. So what I'll do here is that I'll do it with simple circuits here. And then we could also do it with Thevenin, because I know some people have tried it. So we should do this multiple ways. So this was my first approach. And this is the way I sort of like saw it in my mind. And it goes something like this here. So I know this is 5 volts. I know that's ground. So I clearly have a current going this direction. And one of the things that I'm really surprised here is that when you get a current direction, keep that current direction. Please do not change your convention once you start it. And that was the downfall of some of you. So just be consistent, right? So if I follow the current, we gotta agree that if this is ground right here, the current has to be going. Since there's no current there, then the current has to go up. And as it goes up, it splits right here, right? So what I'm doing here is that I'm sticking with my sign convention. So let's apply what I say is simple circuits. By the way, I talked to quite a few EEs in the last week. And we're talking, the two schools that have really heard this again and again was Cal Poly and Berkeley. They stressed the hell out of Thevenin in solving these problems. And they all said that they use simple circuits because it was just so much faster. And so, but apparently that's the way they're stressing. But let's look at this. So this has to be 5 volts. If that's 5 volts, I know that this guy is ground, so this node here has to be 0 volts right there. So I'm going to follow the current. So let's label these currents here. So I'm going to be imaginative, and I'm going to call this I-40. And I'm going to be calling that guy I-80. So I'm immediately just always following the current. So if I follow the current here, that means that this current has to equal these two currents right here. So then I'm going to apply KCL at node A. And I'll call this node right here A, just to be clear. So if I follow this guy here, I should have what? The current across the 10K must equal the current of the 40 plus the current of the 80. Now note that because this is Vx right here, this node here, I'll call node V here, but the label should be Vx. But just to be systematic here, if that's V, then I could see that this node here has to be Vx. If that's Vx, then that node must be the same as this node right here, which is Vx. Okay? So just by looking at the circuits, that voltage Vx must be the same as that voltage right there. And then the other one that I should focus on is this guy right here. There's only one more node here. So what do I call that? I don't know. How about V0? Okay? So now I've identified all of the nodes. Now I'm going to apply KCL again and again and again. So at node A, I have these guys here. So now, what's this current? You can see that's 5 divided by 10K, which will give me what? 1/2 of a milli. We already know that it's milliamps. And then I have the current of the 4K. Now note, I'm just following the direction of the current, right? There's no current here, so that guy has to be 0 minus Vx. So it's got to be 0 minus Vx divided by 40. And then I look at the 80 here, and it's got to be ground minus V naught. So it's got to be 0 minus V naught divided by 80. So when you look at this equation, I have one equation in Vx, one equation in V naught. So it's just systems of equations. So what do I got to do? I get another equation that has to connect V naught and Vx. So the question is, how can I make that connection? I made the connection here already. So the only place here is at node B. So then if I look at KCL at node B, that means that the current coming this way must be the current coming that way. Now remember, some of you would say, yeah, the current's coming this way, but now the current's going that way. And I'm going like, what the hell are you telling me? Right? There's no current in this branch. So that means if I have a positive sign, I'm going to assume this is positive. So therefore, this current must be the same as that current. I can't have that current and that current simultaneously. So you got to be aware of these little details here. So in this case here, I'm going to assume that the current is going this way. And note that they're asking me to solve for that current IC. I don't know the direction of IC. But I'm going to make the assumption due to this positive sign, so I'm going to call that IC right there. So here we go. So the current IC has to be the current coming in here, has to equal the current coming out there. Remember, what's driving me? Those two variables. I need a second equation with those two variables. So there I go. So what's the current coming in? Has to be what? The initial minus Vx divided by 20 has to equal this guy right here, which has to be Vx divided by 40. So now what you're seeing here is that I have what? Two equations, two unknowns. So then we just got to clean this up here. So now I just got to solve for Vx. So probably the easiest thing is to multiply through by negative 80. If I get negative 80 and I multiply the whole thing here, I should get V naught plus 2Vx minus 40. So I should get V naught plus 2Vx equals minus 40. And then if I look at this guy here, I'm going to do the exact same thing. I'm going to multiply by 40. So I'm going to get 2V naught, and then I get minus 2Vx. Then that 2Vx I'm going to bring to the other side. So then I should get 3Vx. So then I should get 2V naught minus 3Vx equals 0. I think that algebra is right. Am I right? Okay. So now I just have a simple system. I'd probably matrix this in my, when I first did it here, but I'd probably do what? And then add. So if I add these two, that goes to 0, that's minus 4Vx minus 3Vx equals 80, right? So Vx has to be minus 80 over 7 volts. And if I have Vx, I know that the current doesn't go through here, so then IVX has to be the same as that, so then IZ has to be Vx minus, divided by 40, which then it should give me this value here. Okay, what is that? Minus 2 over 7? That's the way we're done. Now, a common thing here is this. They said, wait a minute. I have this current right here, right? I know what this current is right here. It's 0.5 milliamp. But wait a minute, I got this line right here, so that means that this current here must be, minus, is the same as 0.5 milliamp. No. Why? Because these guys have power supplies. How do you know that there's no, well, we do know that there's no current here in this model. But these guys have power supplies, and power supplies that are not shown in here deliver current to the circuit. So I can't stand here and just say that's 0.5 milliamp going along this branch right here. Yes?
For the reference, like, just don't use that rule. Like you just, I don't know, just like making sure to not use like the same current rules for op-amp circuits, I guess. Just use the voltage rules exclusively. Just
Yeah, and that's exactly what, the way I did it in class here is that I said, just follow the current.
right.
What are the op-amps doing? And then,
But in that sense, you're using the ideal op-amp model doesn't work because by following the current, you get.
yeah, but there is no current across the ground that we can use because we don't have the power supply. Yes.
So what if we put the ground somewhere else?
Then you wouldn't know if that's 5 ohms.
But that is the defined ground. Can I have the picture?
I mean,
But then you would know that knows 5 volts.
yeah. But the current there wouldn't be the same.
Well, then, yeah, all relevant references. Yeah, Yes.
That's what that was.
So I can't take that half million as you're going out of IA and going toward I-40, I-80, and split that and say that I know that the current through I-80 is going to be.
Yeah. And the reason why is because no. I have a voltage source, right? This guy here is my 15 volt. And then I have another voltage source, which is 15 volts there. So these guys are doing what? They're supplying current. So if you're not including these guys into the circuit, you can't use that ground of saying that the current here is the same as the current there. Now, there's another way that people did it, which I thought was good. And to be honest, I never would have thought of that way. And I was not the only one. There was more than one person that did that. In fact, there's probably about 5 or so that did it this way. So the way they did it here is they did it the following way here. They have this guy. So again, we have all of these guys. Am I doing that okay? Okay. So here's what a different group of people did, which I thought was super cool. They applied KVL. And what they did here is that they essentially said here that they went around the loop. I think they picked this loop right here. Is that what they did? I think they did this loop. So when you do this here, clearly I know what that node is. So then I got this voltage, so then they define these nodes. So how should I define these nodes? Let's call this 0. And so when you do this, they also, but the key, so they did this KVL loop, and I won't do this in detail. And so, but what you end up getting here is that you still associate that as ground. You still associate that as Vx. But then I love that they did this though. I thought this was super cool. They did the following thing. If this is Vx, and that's Vx, and this is connected to ground, and that's connected to ground, the current here and the current here must be the same. I did not see that at all. So let me say this again. So they labeled this guy here as Vx, and they looked at that current, and then they looked at this current, and this current was what? Iz. And what they immediately said here is that the current of the 40K here going in this direction. So they did not take the approach that I did using KCL. What they did here is that they focused this, and the key to the whole calculation was this recognition right there. So what they did here is that they said, wait a minute, this Vx has to equal 40 Iz. And then this Vx is then going to be here. And they'll say here that that Vx has to be also 40. It's called that I-40. I would agree. It has to be the same current. But I'm saying I did not see that. The issue here is that you got to be really careful. is that if you just do it this way, you get a sign error. And the reason why you get a sign error is that the current is not going in that direction. So I can't say that that Vx and this Vx are exactly the same. Because if you, like we said before, we already saw that the current had to be going this direction. So therefore, the current has to split here. Right? It has to go from ground down to here. So in this case here, there's an extra minus sign right there. And if you didn't see that, then you have a small error. And you won't get the numbers that I got. And so what ends up happening here is that then they relate that IZ is the same as I40. Yes?
How do you know that the current through the upper 40 resistor is going from
The opposite
ground
direction?
to VX? Because isn't that like a technically like a voltage output from that op amp, so there should be a higher
Yeah,
voltage there?
I guess, well, one, just because what we talked about before.
Yeah, but you can have the current going that way, and then you can have the backer going this way, and then it goes that way, right?
You'll get signed if you do that. That's my whole point. You gotta know what that current direction is right there.
But how do you know that?
Well, I think I'm looking at this guy right here. And intuitively, if I have current coming from the ground, then that means it's gotta be going to a lower potential.
But how do you know VX is a lower potential? Like, can't it be a voltage output that is a higher potential?
Okay, so let me say this. I mean, that's a fair question. Maybe it's just practice. Maybe I'm too practiced, and I said, well, of course I have to go that direction. Yes.
So Vx is the same for both, and the current's going from 0 to Vx on the top one. Shouldn't it be going from 0 to Vx on the bottom one as well?
It does.
Oh.
But I'm using that polarity right there
Oh, I see.
to define that. But so if you apply KVL like that, and then you use this condition, then you get one equation, excuse me, you get two equations with one variable. So now I can relate these two by just looking at that voltage. So then the current here, what they did here is they just did this. Well, I know this is V out. I know that IZ has to be that. Minus this must be, 20K, and then they put that extra minus sign with 0 minus VK. So then you get one equation with Vx and V naught, and then you get the second equation with Vx and V naught. And then you get those answers right there. Okay, we gotta move. Okay? Let's go to the next problem. So, so the next one is a first order circuit, but note that it's a constant circuit, a constant source in the circuit. I'm not doing time dependent. I don't think we need to do that. Can I erase? Answer your question about how you know. You have to go back. You have to go back to chapter 6. You'll see that I say that again and again and again. If you take out those power supplies, they're the same. They're the same. Another thing that I found here that people did is that they looked at this current and then they said, oh, this current is being divided into here and here. And they use current divider rule. You can't do that. Why can't you do that? That node is different than that node. So in order to have current divider rule, you would have to have these two nodes be the same, and they're not the same. If they were the same, you could do that.
Would you be able to do it? Oh, no, you wouldn't be able to. Field is like 20. Is there a CDR? Since they're still going to the same.
Yeah, you could have said that IZ would have been V naught 0.6, and that's totally legit.
Okay.
And the people who did the KBL, I think
Funny
two of
kid,
them
man.
did what
got
I
work
was
on it,
talking
too.
about. And I think one of them made this clever observation, and then they put that IZ back into here. So then they got high 40. If you got high 40, then you reduce that. That became your second phrase. Yes.
Wouldn't it be like B naught plus BX over 16? For IC?
Say that one more time. Would it be?
B naught plus BX over 16.
But note that this is already measured relative to the ground. Right? So this guy is really this guy is relative to the ground. So that would have been okay. And note to actually see that, you could do this here. Right? This would be V naught minus Vx divided by 16. And then plus Vx minus 0 divided by 40. And then this guy has to be 20. You'll see that Vx.
Well, the 40, yeah,
That will not cancel. Oh, we're looking at voltages, not current. That's fine. That's a mistake.
okay, it's fine.
So if you, do you see what I mean?
Yeah.
Would you, have you solved it? Well, if you did one resistance, I would not be 12. I'll just give you the right well, you need this one over that. Don't know, but
Yeah, I got to pay.
I'm sorry, that's wrong. What's your
Yeah, you don't.
how did you get it?
I got it.
So,
Is it short? You got 12 minutes over the 12.
Post transformation.
yeah, I was 36. Right? Look at the 20.
Oh, well, it's actually. We're finding out.
I'm just doing the
We don't.
Yeah, I got that. It's easy to find all the sources.
one? I don't see that. No, that one was, yeah. I think that's which the back.
I think this was, oh yeah, that could be quiz, yeah. All I know is that's.
Or sorry, level 12.
Oh, it's just the I-12. I think the quiz problem is finding IL.
That's what I need to do.
Or VLC, or you go like that route.
Good, how are you?
Calculated.
That's a mess.
So that's the part, take out all that, but then when you're looking at
Hey, let's do this guy. You know, one of the things that I found out a lot about the exam here is that people forgot about source transformation. Oh my. It made some problems like real easy. But you know, you decided not to use source transformations. I strongly recommend that you use source transformations when you can, except with that simple circuit or node or mesh model. Because if you don't do after that, you could use it as much as you want. Okay? So what we want to do here is that we want to get that current. And I don't know the direction of the current. So, but we'll get it when we get there. So this process here is that I first note that I have a constant voltage. So that means I can get ILT by using this diagram. Right? I can use that. That means it is to my benefit to write this into a source transformation where I have a current source parallel to a resistor and an inductor. That's what I'm looking for. If I gave you a capacitor equation circuit, what's your job? Is to get it into Thevenin form, right? So try to source transformation the hell out of that thing to make it easier on you. So, there you go. So I'm going to start, and I'm going to get 0 minus. So my 0 minus, I want to go in, and I want to, that means I'm looking for this guy right here. So here I go. There's another thing I got to make sure that we're clear. When you deactivate a source, I don't want to forget this. If I have a voltage source, I deactivate it by putting what? A short. If I have a current source, I put an open. There was probably about 10 to 20 of you SOBs that had that current source, I put a short there. And I'm going like, ay, 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 hombre. Yeah, man, I was going like, no, right? That's a simple mistake here. Make sure you correct that. Make sure you correct that. So, without further ado, let's go on. This guy's not on, so what is it? It's a short. So when I look at this guy here, I'm going to get this guy. And then I have my 12 ohm right here. And this is my 24 ohm. And then I have a short right here. So what should I do immediately? Draw your damn notes. Just make it easier on this. Well, I mean, you're tired? You want to get the hell out of the final? Draw the goddamn notes. Because I'm finding people are doing what? They're doing all these complicated KCL, KVL, and I'm going like, where are you going, dude? Look at that. How many nodes are on this thing? Uno, right? Like uno más, right? Right? If this is 2 amps, then you know that the inductor current must be 2 amps. You don't have to think about that. There's only one node. But people insist on trying to do complicated, like transformations and stuff like that. No, do this. Okay? So here we go. So if that's the case here, so now I'm at t equal to 0 plus. So now I'm going for IL of t. So that means here, so when I look at my circuit, I have this guy. So then my job here is that I'm going to remove this node here. This load. I'm going to remove this load, and then that means I got to go after I short circuit, Rn, 1 over top. That's what I'm after here. So what I'll do here is that when I look at this guy here, well, if I look at I short circuit, I'm going to put a short across this guy. If I put a short across this guy, we could do a couple of things. So note, this is a different circuit right here. And so I'm going to define my plus and minus sign in that direction right there. So that means this guy is going like this here. I short circuit right there. So this is 24, 2, 12. So what I'm going to do, I'm going to do source transformations. I'm going to convert this guy into a source, into a voltage source here. And so note that this guy is going to be in the opposite direction. Right away, you could see that I short circuit has to kill the 24 volt source. The 24 ohm resistor. Okay, so this guy is already dead. Okay, so one more time here. I look at this node right here. And what we see here is that this guy is shorted out. So when I do the source transformation, note that I have a single loop here. Okay, so now I'm going to do a source transformation. So if I look at this guy here, so I'm going to get 12 volts. Now look at the current. The current is going what? In this direction? So that means when I do the source transformation, I'm going to get 12, and then I'm going to get what? So I get 2 times 12 gives me 24, and then I got the 12, and then here's my short right here. So you can see that the current I short circuit is the same as the current across the 12. I get these two guys added together, which gives me 36. 36 divided by 12 gives me 3. So then I see here that I short circuit is then going to give me 12 plus 24 divided by 12 gives me 3 amps. Look at source transformation. Okay? So now, we're looking for Rn and 1 over tau. So what I'm going to do here is that I got to remove this guy here. I got to remove that guy right there. So if I look at my circuit here, I got to have a short. I'm going to have the 24. I'm going to have an open here. And then I'm going to have my 12. And then here's my Rn over here. So what I'm seeing here is that I'm trying to calculate Rn from here. So what do I see here? Now, if this confuses you, by the way, it's easy to get confused. Why? You got so much shit coming at you. Protect yourself. How do you protect yourself? Draw in the nodes, right? And you're getting tired here, so if you look at the nodes here, look what I'm seeing. How many nodes? 2. They're in parallel. Right? There's only 2 nodes between 2 resistors. That means that Rn implies that 24 is parallel to 12. Half divided by 3 gives me 8 ohms for Rn. So therefore 1 over tau is then going to be Rn over L. So this will be 4 divided by 2.
8 over 2.
Yeah. That's all I care about right here. Okay? So then that means then my solution is this then. IL of T is I short circuit, which will be 3 plus the quantity 2 minus 3 e to the minus 4t. In other words, 3 minus e to the minus 4t is my current here, which is in amps. So that being said here, now I'm just going to go out to the 12 ohm resistor now. Yes, sir.
So in the solution, you just got that from the general one of the first order differential.
Yeah, you know, some of you definitely on the exam just immediately started writing the differential equation, which is totally cool. There's no problem with that. But where I found that they had problems is that they really didn't understand what I short circuit was and where it was going. All they had was a solution, which is okay, right? We already know that because of this minus sign, that minus sign essentially implies what? That it's moving up that incline, like I said. It's sort of like increasing in current here. So when I look at this here, if I plot this guy, we see that this guy starts off at what? 2, right? Comes in at 2. And then what does it do? It then increases to 3 amps. It charges like that. Right? That definitely doesn't. But that's not what the question is. The question is what? Calculate 12 ohm. Is it voltage or current? Current. So let's do that. You know, I kind of erased this. But what's the current of this guy? Initially. I just erased it right now. 0 because there is only one node. So right away, I know that at t equal to 0 minus, the current of the 12 ohm resistor is 0 because it gets shorted out. So you should expect a discontinuity in the current of the resistor. If you don't get that, you should start sweating a little bit because it's most likely that you're incorrect. That means that's the time to go back and look to see where your mistake is. But so now what I'm seeing here is that I want to get that voltage right there. I really want this current. Okay, I really want this current. So now, do I know the direction of the current? Well, it's got to be in this state right here. So I'm going to say that this current is flowing like this because of what we said before here. So I'm assuming that the current is going to go down. So what we're interested in is this guy right here. So I want this current of I-12. So how do I get that current? I would use KVL all around this loop here. Now remember, technically I can't use KVL, right? There is no E field in an inductor. Let me say that one more time because this will be the last time I'll ever say that. KVL is not applicable in this thing here. Fortunately, KVL gives you the same answer. Okay? But it's technically wrong. And that's because inductors have no E field inside them. So you got to use Faraday's law. Remember, every time you see an inductor, you have that minus sign. Why? That minus sign does not disappear. I do KVL with these guys right here. So I sum the voltages, and then this guy is equal to the negative of the flux, the integral of the flux. And when you integrate that, it's minus L E dot ds. And when you get that, that's the voltage of the inductor. So what do I do with that voltage of the inductor? I bring it to the other side, and that minus sign disappears. You using it straight up is technically not correct. Moving on. So now what I'm going to do here is I'm going to use KVL at t equal to 0 plus. So look at that. I got minus, plus, plus. So I'm assuming that for my source here, I'm going to get VL plus V12 gives you 12 volts. So what do I got to do? I'm just going to take the derivative of that guy. If I take the derivative of that guy, the constant term drops out here. So then I'm taking L. So it's got to be 2 times S hat of 3 minus e to the minus 4t plus 12 I12 equals 12. Okay, so then I take the derivative of that, that's 0. I'm going to get a negative 4 down here, which cancels with that 4. So I'm going to get 2 times 4. It's going to give me 8 e to the minus 4t plus 12 I12 equals 12. Take this to the other side, divide by 12. So then I'm going to get 12 minus 8 e to the minus 4t divided by 12, which will give me 1 minus 2. Thank you.
The answer sheet says 3/4 for some
Oh,
reason.
that's bullshit then. Yeah, I don't know who's the dumbass that actually wrote that. Right? That's it right there. Okay? So then if I plot this, what's it going to look like? Right? Let's plot. If I plot this, I12 of t, you can see that this guy's coming in at 0. Right? So I'm getting 0 amps for this guy at 0 minus. And then there's a discontinuity. What happens? It goes from at t equal to 0, this is 1 minus 2/3, so I get 1/3. So what does it do? It jumps up to 1/3 of an amp, and then it increases as t goes to infinity to 1 amp. So then, let's say this is 1 amp right here. And then this guy does my jump like that. Does that make physical sense? Well, yeah, that's 0. And all of a sudden, when I add this source, it stops the inductor from shorting out this guy right here. So now, there's current flow. I have to increase in current. Therefore, there I get that. Okay, let's go to the next one. So the next one is the second order differential equation.
Where do you get it?
Yes, sir?
Where is it due from itself?
When I divide, that's
Yeah.
12 from both sides. Is that the question you're asking?
No, I saw it in that. It's like 2 times.
Can I erase this over here? Okay, so should I give you 10 minutes for this guy? Do we have enough time? So, or should I just start it right now? Okay. Okay. I was hoping you'd say that. Okay, so. Okay, so we're trying to solve I alpha t. And what you're seeing here is that the switch is opening t equals to 0. So when you look at the circuit, what you're going to find here is that note that there's no source at t equals to 0. So that means what? Everything that there's no constant source. So immediately I could say here that B has to be equal to 0. The force response is 0 right away. So what I want to do here is that when I look at this guy here, so if I look at t equal to 0 plus, my circuit really looks like this here. By the way, I've had some great discussions with the physics faculty about inductors and capacitors because they always assume that current of a capacitor goes this way. And I told them, bullshit. Right? And I keep asking the same question. If I have current going through a capacitor like this, where this is positive and this is negative, what does that mean? That there's an EMF. And the issue here is that, you know, they get spoiled in essence because they look at one loop. And when you look at one loop, the current this way and this way must be the same, so therefore one current is opposite of the other one, so it, you know, the current is coming off in this direction, it looks like. But I'd say you better be damn careful, right? This is either do or die on this problem. You get that second order differential equation right. Okay, and there's a hint in this problem. The hint is that I told you the current is this direction. So that hint is that direction. That means that this guy has to be going like this. And if this is ground right here, that means that the only reason why the inductor voltage is going this way here is because the cap is that way. So that means all the currents are going this way, that way. Okay? You better be careful with that. So when I look at this, that means that the polarity of all of these guys is determined by that guy right there. Yes?
And
that just because you said the current was going that way? Or?
No, because I'm trying to be nice. Okay? But physically, think about it. Okay? This guy goes to a short. So there's no polarity there. This guy goes to an open. What's the polarity of this cap? Plus, minus. The switch throws open now. If the switch throws open, can the voltage of the capacitor change quickly? So therefore, this whole node up here is positive, and that's my ground down here. And I'm putting this in here just to really say like, okay, be careful with the signs. Okay. Now no, I can't typically tell you ahead of time if the circuit is complicated. I can't really tell you whether this is positive or negative unless I do the whole thing. And to help you out, I'll put that guy and that guy in there. Because I'm not interested in sort of like trying to beat you. I think this is a nice circuit. And we'll see if it's a nice circuit right now. Let's do it. We don't got a lot of time. So let's do this here. So this is what? The current's going this way, that way. Right? So here we go. What are we solving for? The inductor current. So then I start off with what? Remember, I do this, and remember, it's sort of like get yourself into a rhythm, right? Feel your pencil, right? Feel the shoes that your feet are in. That's absolutely bullshit, but that's exactly the point here. So let's do this here, right? That current plus that current plus that current is 0. So then I go IL. What is this guy? This is, oh shit, I wrote 2 amps. 2 ohms, right? This is the 2 ohm right here. This guy is 8 ohms. And of course that's my inductor. So then I go what? That current plus the current of the 2 ohms plus the current of the inductor equals 0. Ooh, current of the cap, excuse me. So then I just keep moving on. So typically I then go like this. C, right? And if I look at this 2 ohm, note that this 2 ohm is parallel to the voltage of the cap. So then I'm going to write 1/2 VC, and then I have the current of the inductor. I have my first equation right here. Let's go to my second equation. My second equation says that VC must be in parallel to the spread. So then I'm going to say VC must be in parallel to VL plus the voltage across the 8 ohm resistor. So let's clean this up. So see that VC? I'm going to bring it to the other side. So I'm going to get what? 8IL plus 4S hat IL minus VC equals to 0. Okay, so now I'm going to matrix this guy out. So I'm going to do a matrix. So if I set up my matrix here, I'm going to solve for, I'm going to make IL my first variable. So then this will be 1, and then I'm going to get 1/2 plus 1/4 S hat. Everything's 0 over here, as we would expect. Okay? So then, I put IL, now I got VS, now I'm going for IL, which will give me 8 plus 4 S hat, and then I have -1. So let's get the solution now. So I take the determinant of this, so I get -1, then I get another minus here. So I get -1, then I got to multiply these together. So how do we do this? Can I just multiply these two right here? Okay, so let's do the square term first. So I get 1/4 times 4 gives me 1, so then I'm going to get plus S hat squared. Now let's do the second order term. The second order term here is 1/2 times 4S gives me 2S hat. And then I do 1/4 times 1 times 8 should give me 2 S hat again. Now remember, am I making mistakes? Probably. You gotta help me out. Then I get the constant term, 1/2 times 8 gives me 4. Let's make sure. Oh, I have a problem. Everything's minus. Okay, so you see this? Plus, minus. Okay? So then this is IL, then I'm going to take, do I even have to do the next term? Look at that. I put the 0 here, 0, 0 gives me 0, which is perfect. That's what we expected. Right? So then if I do this, I'm going to get S hat squared plus 4 S hat plus 5 IL equals to 0. And that's a good sign. That doesn't mean I'm right, but that's a good sign. Because that means that I'm agreeing with what I expected here. So now, let's go get the terms. So now if I go get the terms here, I gotta solve that thing. So do I have the roots in my head here? So I have what? 4. Is that right?
Less than number 1, but you didn't change the 4 to a minus.
4 and 1? No, I can't do that. Yeah, I don't trust you right now. Right? So here I go. So I see that 2 alpha over 4 gives me alpha equal to 2. And then omega naught. Dude, that just tells me right there, omega naught is greater than alpha. So it's under that. Okay, it's under that. So that means I got alpha, I needed alpha anyways. So then that means that the solution to the inductor must be what? E to the minus alpha t. Alpha is 2, so I get minus 2t. I gotta calculate omega d first. So then, if I come over here, omega d is omega naught squared minus alpha squared. Oh, nice. So I get 5 minus 1, 2. Numbers are nice. Cosine 2t plus, A1, A2. Yeah, alpha's 2.
So you got.
This 5 minus 4 is 1.
Oh, damn. It's even nicer. Thank you. Like I said, I'm going to make a lot of silly mistakes. Thank you for the help. So I got to go get A1 and A2. So then, I got to determine A1, A2. So if I do that, then that means I got to go solve for this guy. So this equation comes from where? The first order equations. And you can see that there's only one of these guys that includes the derivative of the inductor. So that means that's the one I got to use. So when I look at this guy here, you can see here, so I'm going to get what? VC of 0 plus minus 8IL of 0 plus divided by 4. So you can see that I have to get not only this, but I got to get VC of 0 plus. So now, let's go look at the circuit. I'm going to keep it right here. So I'm going to modify the circuit. So if I modify the circuit here, what we're seeing here is that I have this guy right here. And according to the inductor current here has to be in the opposite direction. So I immediately have to have a minus sign for the inductor current. Okay, so when I look at this, I'm going to put this sign right here by hand and know that I have to have that negative sign. Okay, so I'm going to modify this circuit to save time. So So I'm gonna make this an open. I'm gonna make this a short. So if I look at this guy here, I have this guy going this direction. And I have this guy right here, like that. So you're seeing that the current of the inductor is the same as the current of the 2 ohm. Now note that this resistor, that resistor, and that resistor are all in parallel. Okay, so note all resistors are in parallel. So what am I going to do? You see that 4? I'm going to combine it with this guy here. So this is going to give me what? That resistor and that resistor is going to give me 8/3. So if I look at my circuit here, it's really like this here. So the inductor current is the same as the current across the 2 ohm. The voltage of the 2 ohm resistor is the same as the voltage of the capacitor. So if I do that, so then I really have this circuit now. Where I made this A4 parallel to 4 means that this has to be 8/3 ohm. So my whole job here is to get this current right here. What am I going to use? CDR. Okay, so I'm going to use CDR to get I 2 ohm. So here I go. So it's the opposite resistor right by the sum. So it's going to be 8/3 divided by 8/3 plus 2 times the current source, which is 7, and this will give me I of 2 of 0. So let's see if I can clean this up here. So if I bring this third down here, that's 8, that's 6, so I'll get 8 plus 6 is 14, so 8 over 14 times 7. Okay, that's good. 8 over 4. Okay, I'm going to just listen to you. So now if I got that, I got these values now. So now I see that IL of 0 minus has to be 4 amps, and I see that VC of 0 minus has to be what? This current times the 2 ohm resistor, which will then give me 8 volts. So I have these guys. So now I'm going to plug them right into here. So if I do this, I'm now going to get what? So let's look at this. I get 8 minus 8 times 4. Is it negative 4?
The voltage across the capacitor, you change this.
Change the sign of both of them?
Because we have a negative side.
Oh yeah, that's right. Thank you. Because I had to put this in by. You know what? I don't think that's correct. I agree that this has a negative sign. No, I have to put that negative sign in. I think I agree with Lindbergh here. So there's a sign right here. Right? Because this guy, we agree here that this guy has to be negative. I forgot to put the negative sign in there. Okay, so then that means then that I get 8. Is that 10? Is that right? Okay, so I'm trusting you to help me here. But I'll be selfish because tomorrow, on Friday, you can't help, I won't help you. So, being a smart ass. So that means then I could then go in and calculate the steps. So if I put this all together here, now I have IL. So now I'm going to solve for A1, A2. So this guy is going to be minus 4. And then I have that solution here, which will give me e to the 0. And then I got to put in 0 for my time here. So then I get A1 times 1 plus A2 times 0 tells me that A1 must equal minus 4. And, okay. Let's go to S hat now. So then S hat IL of 0 plus, we already know is 10. So now let's take the derivative. I got to do the chain rule now. I take the derivative of the first term, which gives me negative 2. So I get minus 2 e to the 0 times t equal to 0, which only gives me a1, and then this term will give me 0. So that means then a1 must equal what? 10 divided by negative 2, which will give me negative 5. Oh, did I? Then the chain rule should give me. Oh, okay. Okay, I'm going too fast. So then I get e to the 0, and then I take the derivative of that guy, which will give me a1 sine of 0 plus a2 cosine of 0. So I do get that a2. Thank you for help. So then this gives me minus 2a1 plus a2 is equal to 10. But I know what a1 is. a1 is negative 4, so this becomes positive 8. 8 to the other side gives me 2. That implies here that a2 has to give me 2. So now, what's my solution? My solution for the inductor current is then going to be e to the minus 2t times the quantity minus 4 cosine t plus 2 sine of t. Now, how does this guy jump? I don't know. Is it going down? I think it's going downwards at t equal to 0. Right, at t equal to 0 plus, excuse me, I would expect this to go downwards like this. So if I was to plot this guy, what I'm seeing here, IL of t, this guy comes in, and the inductor current, what was the inductor current at 0? 0.
Negative 4.
It has to be negative 4. So that means it's coming in at negative 4, right? And then it oscillates. How is it going to oscillate? It looks to me, I don't really know, but it looks to me like it's going to bounce downwards. And then what's it going to do? Something like that. Do you see how accurate I was there? No precise. And that's what I expect from you. Yes, sir.
That's what I was gonna ask, how accurate we can draw that.
Let me put it this way. You go through this process, you get negative 8, that looks really good. And then you get this one, no. You got 10, that looks really good. Oh, you got the right form? Perfect. Dude, I do not want to read anymore. I'm really telling you the truth that I am not looking for the fine details. I'm looking for the process. Do you got it down? If you make some major error, I'm going to go like, oh, you got to do that. That doesn't work. But if you got the right idea from start to finish, I think last year, I had something like 15 100s on the final test.
Wow.
It doesn't happen on exam 1 or 2. but it definitely happened on the final assembly. So should I do the phaser circuits now? Do I just jump into it? Okay. You know, that sounds like really. So can I erase this amount of pressure? Can I erase that? Okay, here I go. So what I'll do here is that I'm going to be really loose on these guys. Like, I'm not going to do every single calculation. I'm just going to say that if you do this, this is what you get. If you do that, this is what you get. Now remember, this is all just simple circuits, node/mesh here. We're asking you to use either node or mesh. So when you think about this, what I want you to pay attention to is that what works best for you? Is it node or is it mesh? So here we go. This is this problem 6? So what we have here is we have this circuit right here. Remember that 135 degrees only pays, any, part of the problem solving at the end, not in the beginning. It's only at the end. That means all I'm doing is that I'm adding 135 degrees to the phase right to the beginning. Yes, sir.
These like problems where you say to do it by hand, not by calculator.
Let me tell you, if you do it by hand, it's got to be really, really easy. And I'm expecting that if you multiply it, it will take you faster, I think, to do it by hand than on a calculator. Okay? Does that mean that you're not going to use your calculator? Yeah, I'm sure you are. But you're just going to pretend, and then I'm going to pretend probably that you did it.
So for the phasers, we'll be able to just do it by hand.
That's what I'm shooting back there. Okay. Now, this one here has a little bit of algebra, but we should at least sort of like set it up. It's mostly set up than anything else. Okay? What am I grading on? On setup. I'm assuming that if you had a lot of time, you could just crank them out. Okay? Setup is like the vast majority of the points. So I'd probably say setup has got to be 18 points, 19 points. And if you don't get an answer, or you just make up an answer, I'm going to say, okay, -1. Actually, there's no -1s. It's either like quarter credit, half credit, 3/4 credit, full credit. Actually, I think it's like half credit and full credit, really. But let's move on. So if I look at this circuit here, I have this guy.
Hi. Can I get half credit?
When I was learning phasor calculations, we didn't have those fancy calculators. I mean, phasor calculators. Yeah, phasors with modern calculators. Oh my God, what a beautiful thing. Yeah, doing this shit by hand is not fun. Okay. So my job is just to remind you that this is really all the same stuff. Okay, and what they're asking for here is that they want to calculate this voltage across the cap. So ultimately, this is what we're after right here. That right there. So the first thing that I'm going to do is I'm going to transform this. So note, let's see if we can do some of these in our head here. So the first thing, I'm going to transform this guy into a phasor circuit. So it goes like this. So the numbers have to be nice in order to make it work for you. Okay? So let's see if we can do these on our head. So the one thing you got to remember is that you got to remember this. You got to remember that. The numbers have to be nice. I'm expecting everything to be done in your head. So here we go. So this guy has an amplitude like this, and then it has a phase of 135, negative 135. So that's my voltage source. So now let's do this guy. So the first thing that I'm going to do here is that I'm going to look at that guy. So note, omega is 40. That's 1 over 20. So I should get 2. So here I go. That's the kind of calculations I'm shooting for. When I look at this cap here, you know that I did this really close. So when I look at this cap, what is this cap? So remember, I get a minus J automatically. But then I do what? It's omega, 1 over omega. So then I got 40 divided by 1 over 80. So then I get 80 divided by 40, which is going to give me 2. So this is what I'm really hoping that you do right there. So when I look at this guy here, this is what? 40 into 1 to 8, so I get 8 over 40, so it should be 1/5. So I then should have J 1/5. And then I have this guy here, which is now a phasor current source. And then I look at this guy, and this guy and that guy are the same. And by the way, I'm very good at repeating things like this. So you could just look across the aisle and pick it up. Yeah, is that 1 over 80? Yeah. Oh, shoot. So if that's 1 over 80, then we know what that is. Then that's 2. Okay. So what do I know? I know that this guy is my dependent condition. And what would you do? No. Probably no. Now, here's something, but step back and look at this thing. What I want you to realize here, if I look at this in terms of loops, I have 1, 2, 3, 4. 4 loops, 1 current source, means that I have what? 3 loops. 1 super condition, 3 loops. And then I have 1 DC. And then I have to get this voltage right across here. This is the one I want right here. Yes?
But like, since that voltage is the same as that source.
Exactly. That's one of the things that I was about to say. Because when I'm just thinking, if you just think out loud, that dependent condition here, excuse me, that dependent source depends on that dependent condition. But as soon as I would start to count that up, just say, do I know what that current is? Yeah. Right? Because this voltage is in parallel to that. So I know what I is. So to sort of like separate it, how about if I call that IX here and IX there, just to make it a little bit clearer that I'm really thinking dependent. So one of the things that you should see here is that note IX is known. Because if I look at just plain Ohm's law, right, in phasor form, that guy and that guy are in parallel. So therefore, I know that the voltage across that C must be Ix times minus J2 here, which is also equal to the voltage source. So that means then Ix has to be what? Well, it's got to be that here, so it's going to be what? It's going to be the square root of 2 times the angle of 135 divided by minus J here. So now I got to bring this down to the denominator. Okay, so this is minus J2 here. But what's the angle of minus J2? Or no, I can also multiply by J's. That becomes 1. And then J, we already know, is 90 degrees. And then I just bring it into there. So what I'm saying here is that, note what I've done here. That this is the square root of 2 divided by 2, which means it has to be what? 1 over the square root of 2. I now have this J. Remember, J has a phase angle of 90 degrees. So what am I going to do? I'm going to bring that 90 degrees right into here. So then that means it's this 135 plus 90 minus 45 degrees. That's what Ix is. So in essence, I don't have a dependent condition anymore. So then that source here is just this. So if I look at that current source, you can see then 2Ix then is going to be the square root of 2 of minus 45. So I have no dependent condition anymore. I just have this guy here. So now, what am I going to do? I'm going to say we should use node. Why should we use node? Because I could make this one of my equations right here, one of my variables. So if I was to do this, let me bring out a different colored pen here. I would definitely call this VC. This guy is already known here, right? Because that's the square root of 2 minus 135. So and then this node here, so if I call that C, I don't know, maybe I call this A. And so if I make this my ground right here, look what I have. I have 2 nodes, right? 2 nodes, 2 equations. So with that little step there, now I don't know how nice these numbers are going to be here,